I'm Hello. Okay. We are now. Okay. Welcome to everyone to attend this online tutorial session. My name is Yuhao Wu, and for today's online tutorial session, we will focus on the coding about learning with node labels for the label noise, especially for the label noise. And this coding is relevant to your assignment too. So we will go through all the coding and write something and expand the coding. Maybe this process will cost 1 hour. After I go through all the coding, we have 1 hour Q&A session. You can ask any question. Okay. Uh, now, now let's start today's online tutorial session. Okay, before we go into the coding, I will introduce some important concept about the label noise. Okay. The first is for the label noise, we have uh mostly we have two type of label noise. One is instance dependent and another is class dependent label noise. Okay. And this two type of label noise is the reason about these two types of label noise is based on the generation about the noise. Okay. Uh but for our lecture and tutorial, we just cover the class dependent label noise. Okay. For the class dependent label noise, the generation about label noise is not depend on the instance, it's just depend on the class. So we can build following metrics like the Y is a clean label and the title Y is a noisy label. So based on this clean label and noisy label, we have a noisy class posterior probability and a clean class posterior probability. Okay. The the class posterior probability is condition on the X, you got the noisy Y or you got the clean Y. The probability about you got the noisy Y or clean Y. Okay. And recall the content in the lecture, we can build the relationship between the noisy class posterior probability and the clean class posterior probability based on this function matrix. Because in today's online tutorial, we just consider the binary classification setting. So the y equal to 0 and y equal to 1. Y equal to 0 means it's negative. Y equal to 1 is a positive samples. Okay. We can use this transition matrix, this one, the forward matrix, and for the noisy class posterior probability into the clean class posterior probability. Okay. Uh, if we have this transition matrix, we can build a relationship between the noisy and the clean class posterior, so we can avoid the negative impact from the label noise. Okay, so the hypothesis is how to estimate this transition matrix. Okay. How to estimate this transition matrix? We have an assumption like the arc point assumption. This means suppose we have a point X 0. And in this X0, the clean class posterior for the negative is 100%. The clean posterior probability for the positive is 0. If we have this clean class posterior distribution, and we just input this probability into our formula, we can directly get the first column about our transfer matrix. Okay. So one anchor point x0 help us to calculate the first column about the transfer matrix. And if we want to calculate the second column about the transfer matrix, we use another anchor point x1. The x1. So the x1 is another anchor point from the positive class. That means the clean posterior probability from the positive class is 100%, and the posterior from the negative is 0. Okay, this is the clean posterior probability about the x0, x1. And if we input this clean posterior into here, we can calculate the second column about the transfer matrix. Okay, so the x0 and the x1 help us to estimate our transfer matrix. Okay, so we also get like a theorem like when noisy rate is bound by a constant, the anchor point can be found as following. Like we can find the anchor point, use the noisy plus posterior probability, and if this instance has the highest noisy class posterior, we think this point is maybe it's anchor point. So this is our theory based on our assumption. Like the anchor point should have the highest noisy class posterior probability. Okay. So this is a theorem pipeline about the estimated transfer matrix. Now we go to some coding. Okay. In today's we use the data. This is the input data. It's a CSV, and you can download this data from the Canvas module. Okay. And now we're going to the code now. The first part is about to generation the class conditional random label noise. Okay, for this is a normal process. I like to just import some package. Okay. And okay, before we're going through the code, we have another things like the flip rate. Because today's text is just a binary classification, so we can use a negative flip rate and a positive flip rate to denote each item in the transfer matrix. Okay, the negative flip rate means in the negative class, the probability about the negative class sample flip to the positive class. Okay, so the formula is like condition on clean label equal to 0, and the non label equal to 1, and the probability, the conditional probability. Okay, and the positive flip rate means the clean label is from the class 1, and the non label is from the class 0. So this means the probability about the positive class flip into the negative, non-negative labels. Okay, so this is like the condition on clean label is positive and the non-label is negative. Okay, so this is a definition about the flip rate, and in following we will direct see the flip rate, the negative flip rate and the positive flip rate. Okay. Now let's go to the coding. for the first part of coding is to generate the class conditional random label noise and based on the assigned flip rate. Okay. So now we define our flip rate is 0.15 and 0.25. Based on this flip rate, we want to transfer our data, transfer the clean label, our data into the node labels. Okay. So the first thing we need to, this is our data we use in today. We copy the data because we do not want to modify the original data. So we use a deep copy and get a new data. And the fourth thing, we want to get our label. Okay. Get our label because in our data, the label is in the last column. The last column is our labels. So the label index is the length of new data. And so this is the index about our labels from each instance in our data set. Okay. And we want to flip our clean labels based on the assigned flip rate. So make a for loop. Make a for loop. And the first thing we call the current clean label. Current clean label is equal to transfer the this is our clean label from our data set. Okay. And we want to transfer this clean label into our node labels based on our side flip rate. So we use and this label is should be random generalized. So we will use random. This is a random uniform function from the random package in the Python. And okay, this one will generate the number between the 0 and 1, and we have our flip rate. Okay, so this is decision rules about what times we need to flip our data, our label into a new label, like the 1 minus, this will transfer our current label. Because our current label just 0 and 1. So if we minus 1, so the 0 and get the absolute value. So the 0 label will transfer to the 1, and the 1 label will transfer to 0. So our new label will transfer to the new node labels. Okay. And the transfer ratio is based on our flip rate. Okay, not here. Okay, the following is it's a whole process about like to read the data and generate our node labels. And the following process is to check whether your generated data it satisfies our requirement, like our flip rate. The positive length and the positive flip will calculate which which sample have a noisy labels and which sample have clean labels. And we calculate the negative flip rate here and the positive flip rate here. And our generation data, the flip rate should be very close to our assigned flip rate. Okay. So we can run. Okay. And the test is passed. So this part is about generate the class conditional label noise. Okay. The following is to prepare the knowledge data for training and validation. Okay, I think this is a normal function for our training model. The first function is like to transfer the data into the PyTorch data type. Okay, this is a HAP function. And for this one is to split our data into the training, validation, and test. And the split friction is like the 70% of data is training, and the 10% data is validation, and the 20% data is for test. Okay, you can use the HAP function to split our data. And this function is used in the PyTorch. Like we transfer our data into our assigned training, validation, test, and transfer this data into the data tab in our PyTorch, and use the data loader to call the data when we finish the training. When we do training, we use this data loader to get the data in our training cycle. Okay. So you can direct use this function when you do the assignment too. The second three is to define a simple networks. We just use because this is a simple binary classification task. So we just use just to build a fully connected networks. For these networks, we have the input layer, hidden layer, and output layer. Okay, and the active function we use ReLU. So we need to build neural networks here. Okay, the first thing we need to build we need to use ReLU. Okay. We use function, the ReLU function, and we use because we have defined the input layer. It's a linear layer, and goes through the ReLU function, and have you put this all into the hidden layer, and also use the ReLU function. So we will use two ReLU active function. And we also have our output layer right here with assigned dimension. Okay. And in this process, we have already defined the forward process. Okay, the forward process. And when we use the PyTorch, we just need to write the forward process. And for the back process, it will automatically process by the PyTorch. Okay. So this is our networks. We have input layer and it first goes through a ReLU sorry. First goes through the ReLU active function and then goes through the hidden layer and go to another ReLU active function and go to output layer. Okay. So this one is to assign the input dimension, hidden dimension, and output dimension. Okay, because our just a binary classification task, so the output dimension is 2. And the input dimension is based on your training data, and the hidden dimension you can adjust this. You can adjust the dimension of your hidden layer. Okay. Okay, this is another. So after we define our neural network, we will go into the training and validation process. Okay. Now we have some helpful functions for training and validation. When our random set, the first thing is when we use a PyTorch, sometimes the result is not same when you run. This is because there are some random things when PyTorch compute. So if we want our result is fixed, we can use this function, like to set the random sets, and set the random set like the CUDA environment of Torch. Okay. This function, these things help us to fix the result of every training, every run when we use the PyTorch. Okay. And the next function is to embedding labels to one hot form. Because our label is just 1 and 2. And we need to come to one hot, like a vector, and just one element is number 1, and the other is all 0. Okay, so it's a one hot embedding to transform our labels. Use a torch L function. Okay, and this function is about to calculate the accuracy. Okay, to calculate your prediction with true labels. Because we can access the true label and the model give us a prediction and calculate the accuracy with this function. Okay, and this function is to record the some important things when we do the training, like the array sum validation to help us to monitor our training process. Okay. And this load model function is to have us to input some configuration to compare the configuration when we train model. Okay. So this is some operation have functions. Okay, and training and validation function. Okay. This function is like our training process where we use the PyTorch models. Okay. First things when the model can switch the training mode, we need to define this the training mode for model. And we have a for loop from our use the training loader. because training load can return the training data. Okay, and we transfer our data into the device because sometimes the device is CPU, sometimes the device is GPU. Okay, so for the device, we have already defined our device uses GPU. Okay, and prepare them. And this model is our defined previously, and get a prediction. Okay, and calculate the loss with our assigned labels. And this target maybe it's noisy labels. Noisy label with prediction and use our loss function to calculate the loss. And this is our optimizer. And this function give us the backward about our loss function. And the optimal step, this function, I have to update all the gradients when we calculate the loss, and have to update the weights about our models. Okay, so this is a very normal and very popular pipeline when you define a model and use this pipeline to train the model. Okay, and you can change your model or change your loss here, but the rest of things like the model training and transfer the data into different device diverse and to calculate the gradients and the rest of things is similar. Okay, and for the rest, calculate the accuracy and to print epoch which with respect accuracy. Okay, and this one is validate and test. Okay, we also need to write a pipeline about do the validation. This is very similar with training. Okay, but the important thing like when we training, we use train mode for our models. But in the validation, we use evaluation because in the validation we do not want to optimize our model or update the parameters of our model when doing validation. These things should only be processed in training models, like to update our gradients and to update the parameters, update the weights in our models. So in our validation, we switch our model into the evaluation mode. And we also will need to build a for loop from the validation load. Okay. It's a training load and it's a validation load. Okay. And we also need to use the same process. Yeah. Our data is same as we defined previously. Our data and our labels need to transfer the device side. And but for the prediction, for the data into the model, the important thing is we need to use another function with touch, but no gradient. Mhm. Cardinal gradient. This function makes sure we do not calculate the gradient when we do the validation. Okay. So this coding is very important when we do the validation. Okay. If we do not put this coding before we input data into the model, maybe sometimes it will have some mistake. We will update the weights about our model when we do validation, and we do not hope these things happen. So this is very important. Okay, the torsional gradient, and then the forward is the same as before. Like we use our sign loss function, and we have prediction and target. Okay, and the calculate accuracy is also same as before. Okay, use the accuracy function. And we also need to record the accuracy and the cross entropy loss where we do the validation. Okay. Okay. So there's the training and the validation functions. For this one, we have defined our training function and the validation function. Okay. And for this part is to run our training process and the validation process with our defined models. Okay. Before we run, we have some configurations. Like the model configuration, optimizer configuration, run configuration, data configuration. Okay. For example, like this is a configuration about we do the optimization. We have a set epochs, just train 10 epochs from training model, and the batch size, and our learning rate, and our DK like regularization about training model, and this moment is argumentation about our optimizer. Okay, this change about our learning rate while training. Okay, and for example, this is the configuration of our data. We have our assigned flip rate, it's 0.15 and 0.25, and our training validation test complete ratio and our data path input data. Okay. And this is our run training validation process, the whole process. We define the US. Okay, we check whether we can use the GPU, and we use the configurations, and we set our random set. We make sure every running have the same result, so we set our random set. Okay, and we'll create our directionary, and we'll load data here, and load the model. Okay, and it's our cross entry loss, and now our optimizer. Okay, it's our epochs. Okay, and now we can directly run this code. Okay, we got me select the numpy have no extra long. Okay, so this maybe happen when we transfer the data type.
Hi, I think this might because of the
Yeah,
uh
you can hear. Yeah,
version,
yeah,
right? The version issue.
yeah.
I know
The different
trying
numeration.
to.
Okay, here. Yeah, now it works. And we are training based on our knowledge data, and in our training, the validation and the training accuracy increase. Just 10 apples. Okay, so now we have already finished the code about the training and our validation. And the next part is to evaluation flip rate. Okay, this is similar as to evaluation of transfer metric. Okay, because this is just a binary classification, so I just need to calculate the negative flip rate and the positive flip rate. Okay, but how to calculate these two things? We have illustrated before. We use this theorem. We need to find the sample which has the highest knowledge classification probability, and then we think this sample is a count, and this account can help us to calculate the first and the second column about transfer matrix. Also, it's like to, but now we just we show you the negative and the positive flip rate, and it's similar with calculate transfer matrix. Okay, and you can direct get the knowledge cluster probability through the knowledge labels, like a training model we used before. So we also use the train load, and so now in this part, we will use the model we have already trained before. Okay. But we now we just increase number. Okay, the target is our knowledge labels, and the data is our training data. And we also need to use our model give us the knowledge classification probability. We also need to call this function to make sure our model do not have any update when we do the following process. So output is like the model and the input data. Okay, and the output. This output is like the embedding. So we need to transfer this embedding into the probability. Use the softmax like here. Use softmax transfer output into the probability. This probability is a sample, is a knowledge classification probability of a sample, and this probably have two dimensions. One is a positive classification probability, one is negative classification probability. Okay. And we also can transfer our target into the one hot label. Yeah. Okay. And okay. And from our probabilities, we want to firstly get the positive probability. Okay. Well, this one is the positive class posterior probability, but we need to find our compound, correct? So we need to sort this positive class probability and give us a highest positive probability. Now this guy get a ranking about our positive class probability. Okay. And this ranking is it's like the increase ranking. So the positive flip rate is equal to the mm, mm. Okay, so this is the calculation about our flip rate. We get a ranking based on our positive class probability and found the highest class northern class probability and use this northern class probability to calculate the negative and positive flip rate. Okay, we can check this result. This is our assigned negative flip rate, and we have the estimate negative flip rate, and we have positive flip rate. This is our estimate positive flip rate. The estimate flip rate is very close to the true flip rate. Okay, and the calculation is based on the model we have already trained before. Okay, so now I have already go through the important things about the label noise coding. Okay, if you have some questions, feel free to ask me. Okay, you can direct mute unmute yourself and make a question.
Hi. Can I
Hi.
ask a question? Yeah,
Yeah.
in this example, we don't have the transition matrix, right?
Yeah, because this is just a binary classification task, and we just have you to calculate the flip rate as a calculation about the flip rate is very similar with calculation about the transition matrix. So how to use this method to calculate transition matrix is a task in your assignment.
Yeah. If we can use the post-conditional property here, the same method to get the anchor point. So when we get the anchor point, do we need to scan all the samples to get the anchor point, or we just could sample from it? Because there may be existing many anchor point. So so
Many anchor
my
points,
question. So my question is, when we get the anchor point, do we need to scan all the result or the sample size? For example, for the data set we got from the assignment, it's kind of like the training data set is kind of like the 16,000. So we need to compare all the result probability of each class and get the anchor point, right?
Yeah.
Yeah, so do we need to scan all the results of the 60,000 samples?
Just for that size, the 16,000 is for your training.
Yeah.
So for the definition about the anchor point is like for each class sample, you will find one anchor point, correct?
Yeah, that's right.
Yeah. Yeah, so this depends on your class. If you have 10 class, maybe you need to find the 10 anchor point. Yeah.
Okay.
So if we weight the loss use transition matrix, it should be added into the accuracy functions. Just reweight the loss, like adjust the loss. Okay. Hi, Cat Young. For your question, so if we reweight the loss use transition matrix, it should be added into the accuracy function.
Yeah, hi. I have a question regarding
Yeah.
to where to put the transition matrix to adjust the probability
Okay.
and then to calculate the loss.
Okay.
You know what I'm saying, right? No, yeah.
I got your question. Because our transition matrix can see here is our transition matrix, correct? And our transition matrix multiple our clean posterior probability. Yeah. I think the figure in the chat. Maybe I need to show you the slide. Yeah, slide like here. Yeah, like here. The T is our transition metric, correct?
Yeah.
And then we have our X, and then the X, this is a module we're building, correct? And after softmax, we got the knowledge class posterior probability, correct?
Yeah.
And this is a clean posterior probability. And our clean posterior probability multiple with the transition metric, we will get the knowledge class posterior probability, correct? And
Yeah.
this knowledge class posterior probability can direct apply with our knowledge labels, correct?
Yeah.
Yeah, so when we do a training, we just use our knowledge class probability and to calculate our model. This is our training process with our estimated transition matrix. It's our training
Yeah,
process.
I can get this.
Yeah.
My question is in the code. So if I want to add this computation, adjust probability using the transition matrix, should I add it to the accuracy function in that code?
Yeah,
Is
you
that
need
correct?
to use the accuracy function. You can direct calculate the accuracy function, use a knowledge posterior probability, because this can help you to monitor the training process. But when you do a prediction, like the test, you can direct use this part, use your training model. The training model directly give you the clean posterior probability. So calculate accuracy in training validation. You can calculate the accuracy direct on the training and validation.
Okay.
Yeah.
I'm a little confused here. When we input the X in the, can I draw here? When we input the X in the neural network, we got the P primes here. I think the P primes here, why the P primes here is the clear class posterior, not the noisy class posterior.
This is the assumption. We think this will
okay.
directly return the clean posterior probability, and the clean and the multiple with the transition will give a knowledge class posterior probability, and this knowledge can direct calculate with our knowledge labels because we only can access the knowledge label. So if the transition metric can be estimated the fact, this probability should be the clean class posterior probability.
Okay.
Yeah.
I think I got some idea. And can I also ask, in the in the below there is a minimum.
Yeah.
There is there is the loss function here. So what's the loss function? It is.
Maybe this is cross entropy loss function. The LCE,
okay.
this is the cross entropy, and this is like to transition matrix, transition matrix multiple with clean posterior with not labels, and you need to use alpha mean the loss value.
Oh, okay.
And theta is parameters.
Oh, theta is the parameter.
Yeah, it's parameter about of the model.
Okay. So we might not use it in our code, right?
If you directly use like the PyTorch, and like here, if you directly use the PyTorch, yeah. If you directly use the PyTorch, like this loss function, you see this loss function. This loss function is a cross-entropy loss function, and then use the loss backward. It's actually works on this formula, like here, found the argument, because and the ultimate step to update our gradient. To coding actually is to finish this process, like find the algorithm parameters which can minimize our loss value. And this cross-entropy loss, you can define this loss function.
Okay. Okay, I got some idea. Maybe I can move on.
Yeah.
Thank you.
Okay, is there any question? Okay, if you guys do not have any question, I will finish this online tutorial session. Okay, thanks for your joining today's online tutorial, and I hope you also have a good score in your assignment too.